of class n plus 1 is 1 minus p, and the amount of work actually is the same as the previous one because we compare n times, fail n times. So now all we need to do, according to this, is sum over all the classes from 1 to k, the probability times the time complexity of each of those. Quite simple, and here it is. So we're going to do this. Nice and large. Okay, so what we're going to get is we're going to take the average complexity. We're going to go from 1 to n plus 1. Why n plus 1? Because n plus 1 is how many classes we had. 1, n plus 1 failure. N ways to succeed, 1 way to fail. Total of n plus 1 classes. So we will sum over all the classes the probability of that class times the time complexity of that class. So we will now split this summation. The summation goes from 1 to n minus 1. We will take the n plus 1 out, and we'll go from 1 to n. Why are we doing that? Because pi is the same for all the first n classes, which is p over n. But the probability for the last class is 1 minus p, so it's different. So I wanted to separate that term from these guys over here. So I still have n minus 1 products. It's just that n of them are in the summation, and I add the last one outside. So now I can put the summation p over n is my probability for the first n classes times I. How come I have I? Well, that's very easy, because you can see if I succeed on the first, I do 1 work. If I succeed on the second, I do 2 pieces of work. If I succeed on I do I work. So I work because success is basically the number of comparisons. So that's the probability, and that's the number of comparisons. That's the work. That's the characteristic operation. Plus 1 minus p, which is the probability of the last class, times t of n plus 1 of n, which is going to be t of n plus 1 of n, which is n. So this just requires me to do some simple, again, some of the math I'm showing you here, we'll go through the math also. We'll do a lot more math than that, but this is just a nice beginning. But if you're a little bit lost on this, don't panic, because we will go through how to do all these summations. The bottom line is, if you have, notice that p is a probability. Because it's not a function of I, which is the changing index, that p can go out in front. Actually, the n is also not changing with I. It can also go out. So really what we have is the summation of I multiplied by p over n. And the summation of I is n times n plus 1 over 2. And here's my p over n coming out. When I multiply the summation of I, which is n times n plus 1 over 2, the two n's cancel, meaning the n produced by the summation, the n produced by the summation here gets canceled with the n that was pulled out. That's the n, that's this n right here. They cancel. So I get p times n plus 1 over 2 plus 1 minus p over 1 minus pn. And so therefore, when I see the box on the here, the box is simply saying that that is the value of that. That's the average complexity of that algorithm with probability p. Let's see if it makes any sense. Let's say the probability of finding the element in the array was 0. If the probability of finding the element in the array is 0, that means what's 0? If the probability is equal to 0, then what variable is 0? Then p is 0. If p is 0, then this numerator is 0, this whole term is 0. And therefore 1 minus p is 1. And so therefore it says if the probability of finding the element in the array is 0, then you will do exactly n work. Well, because you're going to compare n times and you're going to fail n times. That's your expectation. Now, if the probability of finding the element is 10%, think of it this way, you're going to do 90% of n, and you're going to do 10% of n plus 1 over 2. Well, what the heck is n plus 1 over 2? N plus 1, just think of it as, forget about the plus 1. What's n over 2? Half. Half. So n plus 1 over 2 is basically approximately half. So if p is equal to 1.0, certainty, then 1 minus 1.0 is 0. This term goes away. And if p is 1, then the amount of work you're going to do on average is n plus 1 over 2, about half. So you're going to find the approximately in the middle. Why in the middle? Because we're looking for the average complexity. And we said the probability of finding the element in each location was equal. But we could change that assumption. we can make the probability decrease as we're going this way, or increase. And that will change our average behavior by using our assumptions. This is what we get. And do I have any questions about this?
How have we done P?
Too small. Just fill. If you know you got to get just think it's more cool. You can get that from everything. Yeah, question.
How have we done P?
Oh, well, that depends on the situation. That's a good question. How do we know the peak? The answer is I don't know. But for example, let's say I'm always searching my data, and I find out that from 3 months of experience, I find that 25% of the time I'm finding things 75% of the time. So sometimes from historical observations, sometimes from data analysis. So we may have that information. Maybe we find that half the time we do, half the time we don't. P is 0.5. What if we had no idea what it was going to be? You could say, well, you could ask the person who we're implementing this algorithm, what do you think is the likelihood? Use something that they're using. You can say, well, here's the worst case scenario. Scenario is P is 0. And therefore, your worst case is n. Your best case is 1, n plus 1 over 2. Okay? So you can give them a range of values. So you can this is worst to best, because basically there's nothing in between. It's 0 to 1. That's what you have. Okay. So now, what I want to show you, I want to change the algorithm slightly. And what we're going to do, and I'm going to try to wrap it up in 5 minutes. I know I'm a little bit long, but what we're going to do is we're going to change it a little bit like this. The data now is going to be ordered. So it's going to be smallest to biggest. So I'm going to say the probability of finding what I'm looking for is still equally likely anywhere. But suppose my data starts at 1, 5, 7, 18, 35, 108, 2000. So if I'm looking for, let's say, an 80, and this element is a 75, and this is 90. Once I look at the 90, what can I say? Once I look at the 90, you're not going to find it because the data is increasing. You're looking for a 90. You're looking for an 85, and this is a 90. It can't be here. So that means I can. So what that means is, okay, so what that means is not only can I succeed anywhere, I can now fail anywhere. So for example, let's say the first data is 10, and it's increasing. I'm looking for a 6. I compare 6 against 10. Not a match, and you'll never see a 6. So I can fail here, I can fail here, I can fail anywhere. So what happens is I stretch that failure from that one instance to failing anywhere. Before I can only fail at the last position, but now I can fail earlier because the data is in order. So now you can see what's going to happen. The instance is match, 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 or x is less than a sub 1. See what I mean? So we can stop. No, so we can succeed here, or we can fail here. So what we have is we go 1 through n, work, 1 through n, work. So now the number of classes goes 1 through n, and n plus 1 to 2n, there are 2n number of classes. So now what I'm going to do is quickly, I'll come back with this on Wednesday. Basically, what we're going to have is we will sum probability times the time complexity from 1 to 2n. And of course, you notice that what I'm going to do is I'm going to split them like this. So I'm going to say, I'm going to go from 1 to n. This is the probability of success times the time complexity of success, plus from n plus 1 to 2n, probability of failure times the time complexity of failure. And I'll go through the math later on, but the bottom line is we come up with this. P times n plus 1 over 2 plus 1 minus p times n plus 1 over 2. When we add those algebraically, we come up with n plus 1 over 2, and magically p has disappeared. P has disappeared. Why? It doesn't matter what the probability is. Our average complexity is going to be the same no matter what. Because we can succeed equally likely here, we can fail equally likely here, so the amount of work we will do on average is going to be half, which by the way was the average in the case of probability being 1.0. But here, the probability doesn't have to be 1.0 because we can fail also on average in the middle, and we can succeed on average in the middle. succeed in the beginning, sometimes we succeed further on, sometimes we succeed in the middle, sometimes we succeed in the end. If they're all equally likely, if you add them up, you're going to get those averaging out to the middle. Failure, you're going to get an average out to the middle. So the p disappears, and you have this one. Okay.
So we don't need the P.
If you multiply this algebraically, you'll see that the p disappears. Because you have Pn plus p, and then you have n plus 1 minus Pn minus p. The p's will cancel out. Everything over 2. Okay? So we'll pick it up from here on Wednesday. Lots more of this coming, and then we'll get into some nice math stuff that I think will be fun. I'll try to make it fun. Okay.